So remember that our okay, let me talk to this first one, and I'll give you another minute or two for the second. Let me talk to the first one. Let me talk to the first one, and if you're still if you want to whisper, that's fine. So I'm going to talk to the first one. So remember that we've got an accumulation function. Our approximate accumulation will be piecewise linear. Piecewise linear formed by actual points on the curve. So we're going to have adjoining those 2 points, adjoining those 2 points, joining those 2 points. So you're going to have, these are supposed to be line segments, supposed to be. It's hard with the pen, there's not a lot of friction on this, so it's hard to. Okay, so these are line segments. Just imagine with your mind's eye. Line segments joining points on the curve. So you get a piecewise linear curve that is trying to be the exact accumulation function. Okay? So this is how we can get an approximate rate function. Why? Because then each piece has a constant rate of change. Okay? So these constant rates, first of all, are they positive or negative? Positive, because y is increasing. Y is increasing on each one. And then are they positive, getting greater positive or lesser positive? Greater positive. So maybe our first one is pretty close to 0. So maybe the first one's like this. And then the next one is a little bit greater than that. You know, if you put that one up here, we don't have any scale on this y-axis. This could be in thousands. This could be in hundreds. This could be in 10 hundredths. Okay? Then the next one, so each one is positive and greater than the one before. Who knows? So each constant rate is positive and greater than the previous. That's all we know. Questions on the first one? So we imagine how are we going to get a better approximate accumulation and approximate rate function from this? How are we going to do better? He wants h smaller. Agree? Yeah, h smaller. So we're not going to do that, but just imagine when h gets smaller and smaller, these segments will do a better job matching the approximate rate accumulation function, and then those segments will get smaller, and some kind of graph will start to form, and who knows? At this point, we don't have any numbers or functions to work with, but so just something like, according to the way I drew mine, something like that. An increasing positive rate of change. An increasing positive rate of change. Okay, so I'll give you a couple more minutes on number 2. A couple more minutes on number 2.
We can't say that has to be going to change there. In that way, like it's there right now. But here it's actually
Okay, are these rates negative or positive? Negative. And getting more negative or less negative? The most negative is the first one, and then they're getting less negative. So are those rates increasing or decreasing? Increasing rate of change or decreasing rate of change? Increasing, getting less negative. So the most negative one over here will be the first one. Who knows, maybe here? Then each one, they're negative but less negative. What do you see about the ones at the end?
They're closer.
Yeah, it's like there's not much of a change at all. So these last couple. So maybe something like this, right? An abrupt change in rate could be the rate's changing quickly, increasing quickly at first, and then it's increasing slowly. These have almost the same rate, so it's something like that. Okay, so that's kind of review, just and make sure we have the concept. We're going from exact accumulation to approximate accumulation, which is piecewise linear, which allows us to make constant rates. And then we can, who knows, something like, something like this. Without numbers, it's just rough sketching, but the idea of that is really important. Any questions on page 1? Okay, so at page 2, another example, but we're going to look at it more in depth here. So page 2, it says, sketch F's, we're going to do one at a time now, one letter at a time. Sketch F's approximate accumulation function on the right coordinate plane using h equals 0.4. So which graph is rate of change, right or left? And accumulation is? Right. Okay? Rate of change on the left, accumulation on the right. You're going to sketch, just like you did before, sketch the approximate accumulation function for h equals 0.4, like I'm showing there. Okay, we better be good at this now. We've done it a couple times. Okay, so here's a dynamic version of what you should have drawn. Showing it as x varies from 0, right? As x starts varying from 0. That's how we always think about these graphs. Even though we see them statically, we think x increasing through intervals of h, and then whatever function we're dealing with is emerging for increasing values of x. Okay, questions on part A? Okay, so now, without notes or book, can you, if the exact rate of change function, exact accumulation function is f, and our interval is h, can you write the equation g for this purple approximate accumulation function without your book or your notes? Who can do it?
So you're not going to be able to just use that. It's not simple. Just as we said, you can't do it all at once. Just do it for this first one. I'll do like that's all he says. Right? So you need to write the equation. How do you all need to yes.
Okay, here it is. Should have at least started making progress on it. That's it. Starting value of y plus this whole thing is what? This whole thing right here is what? What is that whole thing, that whole first term, that big fraction times x minus left x is what? Change in y. Change in y. Which is calculated by? What's this whole first thing here? M. That's M. That's the rate. That's the change in y coordinate in this any arbitrary interval divided by h, the change of the x coordinate. And then what's this right here? Dx. X minus left x, dx. So it's starting y plus the change in y, and the change in y is calculated by m dx. We've seen it 100 times. Okay, next part. On the left, sketch the approximate rate function associated with g if you haven't already. So now, the g function there in purple. So this is just like page 1. Analyze those constant rates and then sketch those constant rates over on the right. Left, sorry. Here you could actually do some decent approximations. You've got some numbers now, right? You've got some numbers. You've got numbers on your x scale and your y scale. So you could actually approximate exactly where, not estimate where these steps are, okay? Okay, what's the value of the first step? About, estimate for the first step, constant rate. 0. No. What do you think? 10-ish. Why? Change in y is 4. Change in x is 0.4. Change in y over change in x? 0.4 over 0.4. So watch it. There it is, 10. Can you do better on the next two? Estimate the constant rates for the next two intervals, and then sketch it. Just really rough estimate. What do you think? Change in y is about what? Just real ballpark.
4.
Almost 4. Change in y is? Change in x? 0.4. So, what do we think? About 4. See what we're doing? So we started making this approximate accumulation, and now we've got a constant rate of change. So to calculate that constant rate of change by accumulation, it's going to be the change in y, 4, over the change in x, 0.4. So that's a constant rate of about 10. Then the next interval. It looks like the change in y is like 2. Why were you guys saying 4? To me, it looks like about a change of about 2. Is that right? Change in y is about 2? 1.5. Some people were saying like 4 or something. Okay, the change in y is like, it's about from 4 to 6. Very rough ballpark. Over the change in x, which is 0.4. So then what do we get? Why am I losing it here? 2 over 0.4? Less than 2. So 1.5-ish. Okay. Less than 2 over 0.2 is going to be something less than 5. Okay. Is that we have to leave?
No. It's a haboon.
Who doesn't like a haboob? All right. Okay. Next constant rate is about 1. Is the last one about 1? Okay. Does it make sense? So, how would we write that rate function? How would we write a rule for that blue step rate function? What is it? Can you write down the rate function now? What is that rate function that would define that blue step, those constant rates, that blue step function? If you understand what's going on, there's no work to do. There's no work to do. You just write it down. Yeah. All right. What is it? So if you're tracking, we already did it. We already did it. What is it? This thing, right? M. So it was already part of that. That was to get M. So that's what that function is. It's the M function, or the rate of change function. Okay, so what do we have? We have positive rate of change, but is the rate increasing or decreasing? Positive rate of change that's decreasing. There we see it over there. How can we get a better approximate accumulation and therefore a better rate of change? What do we do to get a better approximate accumulation and as a result, a better approximate rate of change. Smaller h. There's a smaller h. Here's another smaller h. Look at how good the approximate accumulation function is doing now. You can't see any daylight, right? You can't see any daylight between the two graphs. In this view, they look the same. Even better. So what's happening? An exact rate function is starting to take shape as we let h get smaller and smaller. Okay, here's h of 0.005. Here's h of 0.005. Those are still little itty-bitty constant rates. That's a step function. Little itty-bitty constant rates. So clearly a curve is emerging, right? A curve is emerging, a smooth curve, which would be the exact rate of change function corresponding to this exact accumulation function. So what is that? Here it is. Okay, so the question is, what's that? That's a curve now, right? That's a curve. And so it looks like it could be a quadratic or a cubic or a sine curve or E or something like this, right? And so that's what we call a closed form. So what is the closed form? So closed form is like all the functions you've been used to dealing with in your whole math career. X squared plus 3, sine of x, cosine of x minus 2, e to the x squared. Those are closed forms. And so now that we get this nice smooth curve, we think to ourselves, oh, there's probably some closed form function that represents that rate function where this is reflecting more process. This is reflecting more the process of getting that curve. Is there something like relative to a polynomial or a sine or trig function or something that will model that? Okay, so that's where we're going. But looking at it all together here, okay, so again we had our approximate accumulation, gave us approximate rate. And then eventually when we make h small, we get exact rate. We get exact rate. Okay, so now, oh geez. All right, here's the deal. So this process that we've just worked on now for the last couple lectures, and you've been reading about the book, is a literal reverse process from the forward process that we did the last month, and we worked on them for exam 2. Okay? But we actually, to go forward from here, we want to actually change the approach to this. Change the approach to going from exact accumulation to exact rate. So this was good in that it was a literal reversal. Like we just absolutely backtracked exactly what we did. But now we're going to look at this another way. Okay? So here we go. So here's what we're used to, right? Here's what we're used to. An approximate rate based on intervals that we set ahead of time, right? Old way. Here we go. Old way. Okay, now look at what I've started now in blue. Okay, this is going to be our new approach. What's the difference? So the old way, we set delta x at 0.4, and then we let x increase through the intervals. The new way is going to be have the interval stay with x, so that the beginning of the interval is always the current value of x. Do you see that? How the blue h is showing that? Okay, so this is the new way that we're going to use to move forward. Okay, again, what's our goal? Our goal is, given accumulation, to figure out rate. Okay, instead of using the chunky intervals and letting x increase through those intervals, now the interval is going to be roving with x. So the left side of the interval is always x, the current value of x. Okay, so question A, will the resulting rates of change be constant rates that change abruptly or something else? Question A, will the resulting rates of change from this new approach using the blue roving interval? Will it be constant rates that change abruptly or something else? Because that's what we got before. When we made our rates out of the purple curve, we got constant rates that changed abruptly. What will we get now? Talk and write. Go. So now I took off the old way. I took off the old way. Here's the new way. Here's some more help. Here's some more help. Check this out. Same question. Okay, so will the resulting rate of change graph, will it change abruptly, constant rates that change abruptly? Yes or no? Instead, it will be smooth, continuous, okay? So it will look like this. So we're going to get a smooth curve now. So question, is that smooth curve, is that exact rate of change or approximate rate of change? The y values on that curve over there, are they giving values of exact rate of change of our original accumulation function, or are they approximate? Everyone think exact? Let's take a look. So what is that giving? This point right here, is this y value is giving what? It's giving the rate of change of this blue line right here. Is the rate of change of the blue line the exact rate of change of the original accumulation function at that point? No, it's a lower rate of change. The blue line is giving us a lower rate of change. So while we get a smooth curve, it's still approximate, because for this, say, 0.23, your rate of change is lower than the actual rate of change, which is shown here by the local linearity of the black accumulation function. Okay, so it's still approximate. It's still approximate, but it's just a smooth curve. So we want to write now, the approximate rate function. We're going to go a little bit over today, sorry. We're going to call this R2. You're going to do the same thing you did before. It's the same approach, but now it's just, we're not looking at a particular value from 0.2 to the next 0.2. It's just whatever x is, and then the interval starts at x and goes a length of h, giving us our 2 points. Okay? And this will be true for any x value, So What are we doing? We're writing the rate of change for that blue line. So where do we start? We need the coordinates of these points. What are the coordinates of those points, right? So where is x in relation to this interval? Yeah, no, but we don't need left. It is, right? So write down the coordinates of the points. Everyone should be able to do it. X is always the starting value of the interval. The current value of x is always the starting point of the interval. The current value of x. Therefore, what's this first point? What's the x coordinate? X. What's the y coordinate? F of x. The x coordinate is always now the starting point of the interval. It's not in the interval anymore. It's not traveling through intervals. It's always the starting point of the interval. What's the x coordinate at this point? X plus h. What's the y coordinate at that point? So we actually get an easier formula. What is it? Change in y over change in x. No more left. No more left because x is always at the left side of it. The current value of x is the left side of the interval. So you don't need left x anymore. X is not going through the intervals. It's always already the left side of the interval. This is the approximate rate function we're going to use to go forward from here. We're going to use approach 2 from here on out. That will be our approximate rate function. No more left. No more left. Set. I have a little bit of time right now. So like 2:45? Yeah, go on. Look. Why? Because it's finding the rate of change for this blue line through these 2 points. Okay? And so if I zoom in on that point right there, it's going to assign to this x value, that y value is the rate of change for this blue line. Here's the original accumulation function. Here's the line that we're getting the rate of change of. Do they have the same rate of change? No, this is approximating this rate of change. See?
Okay, it says, will the two approaches ever be equal? And I would say yes.
Where?
That's the value of, if the values of left is x.
That's right.
I gotta go to my car. Is there parking over there? I'm gonna grab the car and drive up there. See my questions.
Yes.
Yes,
Is it?
the values of left of x, right?
Because I left my shoes.
So the old way, the left of x would get us
You know, that in the car.
the x value
And I brought a fresh
for the current.
candy. Yeah.
Both. This has got to be 0. Trying to show both here. There we go. So will they ever be the same? Will the approximate rates ever be the same?
And left of x.
Now they'll be the same. Now they'll be the same. Now they'll be the same.
Just for that
because it's
brief
the same,
moment.
right? Just for the when x is at the start of an interval. then they're the same because you have the same interval. Now they're the same. Now they're the same.
Do we have those green
Now
slips
they're
in
the same.
you?
What?
Do we have the green slips and green papers in
No, they're for your notes.
Okay. So write the rule for the rate of change function for this new approach. Oh, you just did that.
That's what we did.
Okay.
So for the new approach, no more left because x is always the left side of the interval. So you just use x, right?
Right.
X is always the left side of this cruising interval. So you know that
There's no more x minus left of x to get the.
yeah. So the starting value is the x comma f of x, and the ending value is always x plus h, f of x plus h. So then you get
That gets our change to
yeah,
1.
you're always for the whole time. This is the starting point of the interval and the ending point of the interval. Always.
Okay.
Do you have more concrete definition for why it's not, or why it will be approximate not?
Look at the picture.
I just like don't know how to word it.
Okay. Because it's still based on a rate of change for over an interval of h, right? And what is rate of change? Rate of change at a moment is for a very, very small interval. So like if we pause it here, again, I'll go here. So how would we find a good approximate for the rate of change at f? Well, we would look at a moment, right? We'd zoom in. And what would we do? We did this at the beginning of the semester. We get a point here and a point here, and we'd find the change in y and the change in x. And that would be like the rate of change of the actual thing. Look at our blue line. It has a lower rate of change. Yeah. Because the blue line is based on this long interval of 0.2.
So we're still finding an approximate